It looks like we can start. Welcome back, everyone. Almost missed the starting time. I think I was zoning out there for a bit. But welcome to midterm week. We're at the halfway mark, so congratulations is definitely in order. I hope your midterm week isn't going too crazy. For us, it's just going to be a kind of an ordinary week. We'll get through work on Monday, Wednesday, Thursday, and then next week we'll have our first exam, so not on midterm week. That means all we're going to be really doing for midterms is on Friday, the 11th, I'll just be reporting your current course grade as your midterm grade. So that's just going to take into account exam one and all the homeworks that are due up to that point. Well, that's the announcement so far. Any questions at the moment? Okay, then with exam one next Monday, the thing that we expect is the coverage. It's going to be on these sections specifically. Section 7.7, this one was approximate integration, so think trapezoid rule, Simpson's rule. 7.8 is the one on the improper integrals. Then sections 8.1, 8.2, this is like the curved surface areas. I only asked one question from this two sections, so it'll either be the length of a curve problem or the surface area of the area of revolution type problem. Then, like we mentioned before, section 8.3, I'm not going to ask a hydrostatic force question on that since I felt the book didn't cover it well enough. But we'll do a centroid problem on that one. Looks like I was able to fit into the exam without making it too long. I think I had to take a problem out. But for the centroid problem, it's going to be the full set of integration. So you'll integrate once to get the area. If you make a mistake, there's partial credit for sure, so no high stakes. You'll integrate a second time to get the x-coordinate of the centroid, a third time to get the y-coordinate of the centroid. And I picked an example where it's not going to get us bogged down on computations. We can move through them. It'll be more about the concept of the formula and assimilating the result. Then from these two sections, these are on testing if you have a solution for a differential equation, 9.1. So you could expect a problem on doing that kind of work. And 9.3 is just solving a separable equation. So expect a problem along those lines. It ends right at 9.3 only because I tend to think of this week as like a buffer week where you still have an assignment that's going to come due on the day of the exam. So it doesn't really fit on exam one, but we still have to go forward so that we don't get behind on the schedule. Other things that are posted here are just like we had on exam one. Version one of the sample exam two problems has some pretty challenging problems, but it's a good set of fresh problems if you'd like to take a look through there. Solutions at the very back. The sample exam problem two, I put here, these are more similar to real exam questions. My emphasis on both of these is just to say some of these problems that are very challenging are obviously cannot be a real exam question. So if you open up version two, these were the old lecture notes and they're still here. All I did is I took out all the formulas. So these are kind of like brand new problems. Unless you have a really, really good memory, you might know how exactly each one of these goes. But you could use this document as a section by section basis, just doing a couple additional problems for practice. The other document, this one here, version 3. Again, these are more similar to real exam questions. These may or may not feel familiar, but if you look at them really carefully, it should feel like deja vu. These are just the homework assignments all put into one big document. The homework assignment problems, they're just as good as really great practice for exam questions. None of them got too crazy. Some of them that might have been a little bit longer are not going to be on the real exam, but this is just another set of problems that you could take a look at, get some additional practice on. Like we mentioned, we'll be doing the same exact pattern on every single exam, and the last page on the exam is going to be pretty much the same on all the exams. It's the esoteric derivatives that are easy to forget, and quadrant 1 of the unit circle diagram for trigonometric evaluations if they come up. Well, any questions at all, folks, about the exam? Okay, but again, exam 2 is kind of a weird exam for our class. Let's just mention this one more time. If you are on this section, the fully online section, then when we go to take the exam on Monday, the 14th, there won't be any actual class, but we will have classes on the rest of that week there. For people who are in this section, we won't have class either, but we'll just be in this class on Monday at the normal class time, just for the purpose of the exam and nothing else. I always mention that because it's easy if you're in the online section to come in on Zoom at 7 p.m. on Monday next week, but we won't have class due to the exam. Scroll back down. This is turning into a long document. But any last questions at all, folks, with any of these announcements? Sorry, say again, Rhett? You're really coming in really quiet. Maybe that's my problem. I just bumped the volume up. Or might have missed something. Any other questions so far? Could have just been an open mic, potentially. Okay, well, let's dive right back in. We've completed the content that's going to end up on exam 2, all the way up to section 9.3. But now we've got to finish off section 9.5. And we're making a big change. Instead of doing chapter 10 next, chapter 11 is often thought of as the harder chapter of Calculus 2. So we're going to do it right now. That way we're finished with it before the end of the course. And we're not trying to finish off really hard topics like on a week before finals. So after we finish off chapter 11, they'll give us another couple good 2 or 3 buffer weeks to work on chapter 10. It's a pretty short chapter, and its main purpose is to help connect what we do in Calculus 1, Calculus 2 with what we're going to do in a Calculus 3 class. But here's where we left off right before, I think the technology started to sputter out. The projector was going off, either a hardware problem, a software problem, or a power problem. I'm not too sure. But this is the problem we were having some technical troubles on, ended about 15 minutes early on Thursday. The way this problem worked, though, was we made a really important observation, and we should always do this for every differential equation that's linear of this form. If you take the derivative of x power 4, you get 4x cubed, the second term. That's what allowed us to take this whole thing right here and declare that's just the result of our product rule. So we put that inside the integral, integrating both sides, and we just get x power 4 times y. So that's the major observation about this example here. After we solved this, most of the work was solving the trigonometric integral. We just isolate y, and that's our solution there to that differential equation. So we'll do a couple more examples along these lines, look at an application, and then move into chapter 11. Were there any questions at all, folks, on analyzing this one? Okay, so we're up to our fresh problem of the day, part C. The issue with part C, I'd say right off the gate, just looking at it, is it's not in the format that we would like it to be in. We would like to have the derivative term come first, then the term involving y come second, and 2x should be isolated on the right-hand side. So our first step on this one is really just organization. We'll go x, y prime, minus 2y equals 2x. Then let me pull something down just for another quick comparison. Well, what was that? The digital ink is not normally supposed to move along with us. That was weird. Let me just fix the X on that. Probably because this document had some issues last class, maybe, who knows. But let's take a look at how this went down with the fresh differential equation here. So if the derivative of the first term equals the coefficient of the term involving y, then we could save a whole lot of steps on this thing. That's what was happening here, derivative of x power 4 becoming 4x cubed. But this time we have a problem. The derivative of x is not equal to negative 2x, and that means we have a totally different approach this time. So what we now need to do is actually isolate the y prime by dividing out x, and write this as y prime minus 2 over x, y equals 2. So we divide all sides of the equation by x. We want a coefficient 1 right by that y prime. And if we get that coefficient, we can say that this right here, the 2 over x, and even more, you have to grab the sign as well if it's negative. That's our p of x function. The whole purpose of observing the p of x function is it's going to give us an integrating factor. So the integrating factor will allow us to undo the product rule, but we first start by saying well, let's actually start a little bit earlier than that. Let's start by writing out I of x. Not that you would lose points if you did write it down on your paper, but this is my way of saying we're doing an integrating factor, I for integrating factor, of x. It's the base e exponential to the power of an entire indefinite integral, negative 2 over x dx, So your p of x function goes inside. We get an antiderivative of that function. It's now e to the power -2 natural log x. Well, we always take the simplest antiderivative when we're dealing with the integrating factor. That's why there's no constant. And also, that's why there's no absolute value. But really, there doesn't have to be absolute value, because right here, once we divide by x, and even right here as well, x cannot be 0 any longer. If there were 0 here, we've wiped out the differential equation. There's no derivative. If it's 0 here, well, now it's undefined, so that's a problem. So that meant x in this problem has to be bigger than 0. Well, you might say, why not less than 0? That's a possibility as well. But from here, x equals 2, y equals 0. So we cannot allow x to be 0, but we need an interval for which we're going to solve the differential equation on. We pick the positive interval because the initial condition has a positive value for x. All of that to say, we don't need absolute values on x any longer. It's just a positive value. Any questions, folks, to that stage? Okay, so this is pretty typical when a logarithm comes up in this context. It won't have an absolute value sign. But we don't want to use the integrating factor in this format either. This would be awkward. It's not going to really help us solve the differential equation. We want to simplify these as much as feasibly possible always, or else equations will get complicated on us. So first thing to do is take that power of -2 with properties of logarithms. It's now an exponent. So it turns into this: e to the natural logarithm of x to the power -2. So the -2, which was a coefficient to the natural log, is now an exponent on x. That looks really small even on my screen. Let me see if I can fix that though. So now it's an exponent on x, and that was really a required step, because what we need to do is this cancellation right here. But the thing that's kind of crazy about that cancellation is it does not work here by the red dot. If there's a coefficient acting on the natural logarithm, any coefficient, positive or negative, no cancellation. Let me focus that arrow a little bit better. Due to the -2 highlighted, there's no cancellation. So we just have to use properties of logarithms to bump the power as a power, bump the coefficient to the power of x. And finally, all said and done, the integrating factor I of x is now x power -2. Let's color code that just to show what we're going to do with that thing on the next step. Any questions, folks, so far with the integrating factor portion? Okay, next, we take that x power -2, multiply both sides of the equation by it. So our next line, we're now focusing over here on the differential equation again. We have x power -2 multiplying y prime times, let's go maybe make -2 over x times x power -2 multiplying y equals 2 times x power -2. So next step is just going to be to simplify some of this stuff, make it more presentable. Here it's okay right where the red dot is, x power -2 y prime. Over here, we need to consolidate base x, divide this x into x power -2, and we have -2 x power -3 y equals 2 x power -2. So this is where we land so far. And now that we're at this stage, hold this thought real quick. Let me pull a screenshot one more time. Shouldn't have deleted it. There's a great check on this. The check looks like the shortcut on the prior problem. The prior problem totally skipped the integrating factor I of x because the derivative of the coefficient to y prime was the coefficient to y. Now we need to check that again. If the coefficient here, upon differentiating, is not -2 x power -3, we have a problem. There's a mistake somewhere. I'll put d by dx just to say we're differentiating. But sure enough, the derivative of x power -2 is -2 to the power 1 less, power -3. That means We could put a check there. We're ready to undo the product rule at this stage, much like how part B started on this one. Does that make sense so far? Okay, so if we're happy with that, then next step is really just going through the motions. From here on out, the problems essentially always go about the same. Start over here, and we can say that this is x power negative 2 times y prime. Then give it a little bit of space before equality is equal to 2x power negative 2. The reason we could do this once again is when you differentiate, you probably differentiate the y first, and you get a y prime. On the next pass, you differentiate x power negative 2, and you get negative 2 power negative 3. The other terms would be copying, so this is just product rule going backwards. That's something you really do in Calculus 1. That's why it looks so weird. You don't do product rule backwards in Calc 1. But in Calculus 2, there's a call for it. Next step, we just integrate exactly what we have. So integrate the left-hand side with respect to x, the right-hand side with respect to x. We need to also recall we have an initial value, so don't let me forget that step. And if I zoom out just a touch, there we go. On the left-hand side, the antiderivative is immediate. X power negative 2 times y. On the right-hand side, we actually do have to integrate this one. Power is going to go up on that to negative 1, and we'll divide 2 by that negative power. So negative 2, x power negative 1, add a constant c. So we've got the general solution to this, an implicit form, but we need the specific solution that solves that initial condition. So let's write over here, y of 2 equals 0. This means if x is 2, y is 0. So using that information, however you'd like to visualize it, I usually put this extra line just to remind myself what we are really conveying right here. Take this information, plug it into that equation, and we get 2 power negative 2 times 0 equals negative 2, 2 power negative 1, plus a constant. So we're just about there at this stage. Any questions so far, folks? Okay, well, left-hand side is pretty quick. We just get a 0. The right-hand side is kind of confusing with exponent laws going in. These are not double negations in the sense of multiplying. Negative 2 stays right where it is. 2 goes down below to the power of 1. So where the red dot is, it's a glorified negative 1. So 0 equals negative 1 plus a constant. Finally tells us the constant must be exactly 1 in order to solve that initial condition. The function evaluated at 2, coming out at 0, requires the constant has to be 1 and nothing else. So it's kind of satisfying to get a unique solution to this. On our next line, all we're doing is plugging in the constant. So we've got x power negative 2y equals negative 2 x power negative 1 plus 1. Finally, oh, that's a negative 2. I don't know where my negative went on that. Last thing to do is just eliminate this term here. You could divide by x power negative 2 if you like, or I think the slicker way to visualize it is multiply both sides this way. Multiply by x squared here, x squared here. Then on the left, you just get the function y, so y is now solved. On the right-hand side, distribute x squared in from the right, you get negative 2x plus x squared. So finally, that's our solution to that differential equation. Definitely kind of an adventure to get to there on this one, but that's partially because we had to do the integrating factor to just kickstart it in the first place. So this is always a good check, even before you start the problem, because not every question requires a integrating factor necessarily. It's good to see if there's a shortcut baked into the problem, potentially. Well, any questions at all, folks, with this one? I solved it for this line mainly, right here. Oh, yeah, absolutely. That'd be a fine way to do it just as well. Yeah, my style of doing it is usually to solve for here. But if you multiply by x squared and solve it at the very end, that's perfectly fine as well. Honestly, it's kind of a pot shot which way is faster. Depends on the problem. Other questions so far? Okay, well, let's try out one other one. Then we'll look at an application and then jump into chapter 11. So here's our next one for the day. Like I need to zoom in on that. This one's using Leibniz notation, but it doesn't matter whether you're using Leibniz or Newton's prime notation on these problems. Whereas in section 9.3, the separable equations, you always want Leibniz notation because you're separating out dy dt. Here we're leaving it just as is, but let's make the first observation that if you took this term, differentiate it, you get derivative of t cubed is 3t squared. So that tells us this one does not require an integrating factor. We can just immediately launch into the solution of this one. So that's always an important observation because you can divide by t cubed. You can form p of x, then do e to the power of the integral p of x, and then multiply the whole equation by that integrating factor, that you end up right back here. So it's like you complete one big circle. Always kind of unfortunate when that happens. So on this one, we can immediately just say it's t cubed times y, the prime on that one. So the left-hand side immediately becomes this, a product rule. Right-hand side is just cosine t. And so we're ready to integrate right at this stage. So let's maybe take an additional step. So we're not doing so much in one step. On the next line, integrate t cubed y. This is going to be with respect to t, so dt on the right. Integrate cosine t with respect to t, so dt on the right as well. I forgot my prime on this one. We need that prime to get a fast antiderivative, or we're just going to be stuck on that all night. So now the antiderivative of the derivative gives us t cubed y. On the right-hand side, antiderivative of a cosine is a positive sign. And we add in our arbitrary constant of integration c. So at this stage, we're just about there. And because of a question earlier in class that was asked by Raquel, you could solve for the constant c here, or just solve for y and solve for c later. Let's go that route just to show what it would look like if you prefer that method. So I'm going to divide by t cubed and get y equals sine t plus a constant, divide by t cubed. Next, we come up here. If it helps, you can say when x equals pi, y equals 0. Use that information to plug in over here. We'll have 0 on the left side. Oh, I did make a mistake there. The variable is not x, it's t. So let me put in a correction for that one. Usually that's not a critical mistake, but sometimes it can be. So it's a good thing to be just careful with that stuff. Okay, so we put in a 0 for y. Now for sine, we're plugging in pi for t. So sine pi plus a constant, divide by pi cubed. So that's how it would be all set up at this stage. First thing we would do is clear the denominator. Multiply both sides by pi cubed is just feeding pi cubed to 0, so still just 0. Is sine at pi. Sine at pi is also 0, plus the constant. So that tells us the constant is just 0 altogether. Coming back over here, we plug in the value of 0, so now we're essentially done. We can say y equals sine t divide by t cubed, and that's the one and only function that not only solves the differential equation, but also has this feature of the function. At pi, we get value 0. What we did, folks, that's our last differential equation of this type before we take a look at some applications. Well, an application. Any questions about how this method goes? Okay, I guess I have a question for the class. What seems to make the most sense, the separable ones or the linear ones? Any opinions one way or another? It's all kind of the same. I would kind of tend to agree with you. I think separable equations make a little bit more sense to me because we work with differentials so long. That's kind of just the heart of the procedure. Think of it as a differential. These are touchy because things have to line up right. And when they don't, you get this brand new formula, the integrating factor you have to work with, changing your method of approaching the whole equation. So I feel like these are a little bit trickier because of that reason. But after you go through them in the homework, they're really not too bad. What's always tricky though is a random application, especially if you're not into the discipline this one might have been in, might have came from. This one looks like it's electrical engineering. So for the folks in electrical engineering, let us know if we're getting any of the constants wrong or thinking about this one weirdly. Even though applications are tough, the cool thing is you don't really actually need to know too much as long as you're able to fill in how the mathematics should go and what the quantities should represent. So here's how this application starts out. The figure below shows a circuit containing an electromotive force. I believe that's supposed to be E for electromotive over here on the diagram. A capacitor, that's got to be the C, with capacitance C farads, so this is the weird units portion, and a resistor with a resistance of R ohms. So there's our resistor. They tell us next, the voltage drop across the capacitor is Q divided by C. I'll just trust them on that, where Q is charge in coulombs. So in this case, Kirchhoff's law gives the equation down below. Hey, folks familiar with Kirchhoff's law? Me neither. I haven't taken electrical engineering type classes, but apparently Kirchhoff's law gives you that. Next, example 3 in section 3.7 had something to say. They said I is equal to dq dt. So they're referring to this right here. That I becomes a rate of change of Q, which is, oh geez, what was Q? Capacitor is Q over C. It's the rate of change of the charge is Q with respect to time. So that's what happens to I. Now they go on to say, suppose the resistance is 5 ohms. They were talking about this part of the diagram, which is that part of the differential equation. So we're just going to plug a constant 5 there. The capacitance is 0.5 farads. So that's referring to this part of the diagram. And we're putting a 0.05 right there in the differential equation. And notice that Q over C got turned into the reciprocal of C times Q. That's because Q looks like it is the dependent variable. That's like the Y. So you have a Y prime here by the red dot, and an ordinary function Y over here as well. It's starting to look like those differential equations. But let's see what else we have. A battery gives a constant voltage of 60 volts, and the initial charge is 0 coulombs. Q of 0 is 0. When it says a constant voltage of 60 volts, I believe they're referring to this portion right here, or plugging in 60 into that location. Well, how does that look to folks? Does that make sense so far? Okay, I feel like a lot of these applications in differential equations where it's a math class, so we're not really electrical engineers, the applications are more about just tying the information together and following their trail of thought when they produce the differential equation. Once we plug all that in, it's as if the context didn't matter any longer. It's just a differential equation with different looking symbols. So let's carefully plug that in. 5 dq dt plus the reciprocal of the capacitance, which is 0.05, multiplying Q, is equal to the value of 60 volts. So that's our differential equation with the information plugged in. We might need a calculator on this one. This will do just fine for now. So let's go 1 divided by 0.05. Seems like a nice round number. Forgot how Excel works. 1 divided by 0.05. Yeah, that's a 20 there. So this differential equation is now 5 dq dt plus 20q is 60. Well, Now that we've kind of extrapolated completely away from the context, it's all about solving this thing now. Our check is, we want to see if the derivative of 5 equals 20. There's no way that's true. The derivative of a constant is 0. But that's our common check we've been doing on the other problems. D by dx is not equal to 20. So let's just say not equals here. That means we need to use an integrating factor on this problem. And that's going to be a p of x, we're integrating, which is just the coefficient to the function q we're solving. So whatever goes here, oh, hang on, whatever goes there upon division is going to give us the right value. Hold that thought, it's not 20. Before getting your integrating factor and building the function p of x, you do have to clear out the coefficient by the derivative. My bad on forgetting that step. So next step, divide by 5, and we have either q prime or dq dt plus 4q equals 12. So now we're in business. Let's reconvene on p of x. P of x is now equal to 4, coming from this part of the differential equation. And before I forget, I think they said the initial charge is 0. So that's an initial condition of q at 0 equals 0. So we're also solving an initial value problem on the top of it. But this isn't too bad once we've gotten started to this stage. Any questions at all, folks, so far? Okay, a lot of our work is just, again, figuring out the context so we know where to plug in the constants or functions if there happen to be any. On the line 2, we checked if we can make this a fast process. We can't, so we divide by 5 on line 3. But finally, this is where it starts to become really solvable. On the next line, we're going to take e to the power of 4. So we're getting our integrating factor back. Sorry, go ahead.
So why does 4 work in p of x when the derivative of 0 is in 4?
Oh, we're going to try to plug in a better function here to make it all work out. So kind of where we're at so far in the progress of this one is, say, like on this one right here, the derivative of what was up front right here was not the -2. So then on our next step, we divided it out. We got to this stage. This is the stage that we're on in our current problem, where there's nothing in front of y prime, and we're about to find the integrating factor using that part as the p of x function. So back down to ours, let's actually take a quick screenshot to compare. Back down to ours finally. Here, this is the stage where we couldn't do too much with this one because the derivative of 5 would have been 0. That's not what we had here. And now that we found, or divide by 5 and have this blank coefficient of 1, that's where we're at here on this differential equation. So we're taking the -2 over x, which is the 4 on this one, and integrating that 4 like we did in that prior problem. Does that make sense with that idea so far? Awesome. So with that as our antiderivative, we're going to get e to the power 4x. Pretty fast antiderivative. Again, we take the simplest antiderivative, so no plus c on that one. What we do with it is we take e to the 4x, we're multiplying it on both sides. Here's where the check with the product rule may or may not work, but we're going to do that next check. It's going to turn into e to the power 4x dq dt plus 4 e to the power 4x q equals 12 e to the power 4x. At this stage, we do that same comparison that we've been doing all along. We have a new coefficient in front of the first derivative, dq dt. So we take a look at this one. If you differentiate e to the power 4x, you get e to the power 4x times 4 through the chain rule. So now this does come out right. Let's say d by dx. A check there, since we do have the right derivative on this step so far. Well, Any questions? Yeah, go ahead. Oh dear. It was supposed to be a T. Thanks for spotting that. I've got something like 4 X's that need to change. Sorry about that. Must be really, really like X's over T's for some reason. But good eye on that one. The actual variable is T. I think this is the second mistake of that nature this so far. Thanks for spotting that one. So e to the 4t, 4t, and 4t there. Other questions at the moment? Okay, with our real variable in t as opposed to x, we're now ready to say this next step. Take e to the 4t, multiply it by q, put a prime on it, and that's the entire left-hand side now. You can double check if you differentiate q, that's dq dt, e to the 4t copied. If you differentiate e to the 4t, that's the 4e to the 4t, and q would copy. So our left-hand side is ready to go. Right-hand side is just 12 e to the 4t. And I think we're ready to integrate. So full integral of the left-hand side with respect to t, so dt. Same with the right-hand side, new dt gives us, this is getting kind of crammed on space, so let me just carry it down to the next page, as well as the initial condition. So on the next step, we liberate everything that was differentiated and just get e to the 4t times the unknown function q. Over here on the left, if we integrate this, we would just get 3e to the 4t plus a constant. The way that worked is derivative of e to the 4t is itself. Then the chain rule says differentiate 4t to get it times 4. So 3 by 4 gives us the 12. And really the kind of the way I analyze these is we know we're getting e to the 4t from there. If there's a coefficient of 4, we don't need to do a u substitution unless it's like t squared, square root t, something more involved. All we've done is taken the 4, divided it into the 12 to get the 3. So next step, we'll get the initial value. This one's not so bad. It says when t equals 0, q equals 0 as well. So plugging that in, we get e to the power 0 here, times 0 for q, that's kind of nice. Here we get 3 times e to the power 0, plus a constant. So that means the left-hand side is 0. The right-hand side is just 3 plus the constant. And so the constant must be -3. So we've got a value here now. So a couple more steps. We have e to the 4t times q is 3 e to the 4t minus 3. So we've substituted in the constant. Last step is just to divide by e to the 4t. And notice we always get an explicit solution for these first-order linear equations, provided we're able to get a good antiderivative on this thing here. So we've got our solution. The charge in that diagram up above is q. Let's call it q of t. We really have solved for a function. You don't have to. It's more of a stylistic choice. Here we're emphasizing the function. It's going to be equal to 3 minus 3 divided by e to the power 4t. So just divide everything by e to the power 4t, and we've got our solution. So thanks to Kirchhoff's law and the things going on in this diagram, with the values given, the initial condition, the charge at any time t is that function. It starts off at high charge, but as time gets higher and higher, this goes to 0 really rapidly due to the exponential function in the numerator. So it looks like it starts off at charge 3. Or hang on, let's think about that. Actually, that one's a good one to plot. Let's take a look at this a little bit more. It is an applied problem, so we should see if it even makes sense in the first place. So let's plot our function. Let's call it f of t, or x rather. Think of these as x's, 3 minus 3, e to the power 4x. And this is what the charge is doing. Looks like it starts at time as 0. It rapidly increases to a charge of 3, and then the machine carries on as before. That makes sense, right? You turn it on, and then something happens. It rapidly, the whole system reaches the charge of 3, I think it was coulombs. I guess that does make sense when you think about it. Well, any questions at all, folks? Maneuvering through that applied problem? Okay, well, let's save this up. And we did it, folks. That was Applications of Integration, Chapter 8 and Chapter 9. Differential equations is really just applied integration, essentially. Now we're switching gears in a pretty major way. We're going over to Chapter 11. Chapter 11 is all about sequences, series, and power series. But we're going to start off Chapter 11 by just saying, why do we need Chapter 11? I think that's probably the larger question there that needs to be resolved. Starts off with the fundamental theorem of calculus, part 1. You notice we state this a lot, and that's because we use part 2 so often, we take it for granted. And then we forget that part 1 is really pretty weird. Part 1, in essence, is all about producing an antiderivative. Let's see if we can make sense of that statement. Oh, what did I just do? What in the world? Can I Control Z that? Yes. Okay, I'm not too sure what keystrokes did that, but I'll just try not to do it again. So this is how it goes. We know if you have a continuous function on a closed set, this information enough alone guarantees an antiderivative. So one exists, we can find it. So take a continuous function on a closed domain. We define a new function g. In this way, it's an integral function. We're integrating from some domain element A. It doesn't have to necessarily be one end or the other of the closed domain. It could be in the middle. But integrate from some constant in the domain up to x of the continuous function. And this, there we go, this is an antiderivative. The reason that's true is if you differentiate this function g, this is the real content now of the fundamental theorem of calculus part 1. The derivative of that function g produces the integrand. But that equation alone is telling you you truly have an antiderivative. Let's just say, to emphasize, g is an antiderivative of f. So no matter what the function f is, we can find an antiderivative in that kind of way. We almost never do that because all the antiderivatives we've been going for have been solvable. But here's a problem where it's not. If you've done the reading, you've probably heard our author's discussion on this one. This is just one example of a function, and there is a plethora of other functions that have no closed form answer for its antiderivative. What I mean by that is I can't find the antiderivative by writing down a finite number of terms involving multiplications, divisions of algebraic functions. It's just impossible on this one. That's pretty weird. And what's even weirder about this, that kind of equation, e to the x squared, can come up in applied settings, just like the circuits diagram we were analyzing. It can come up from really simple origins, solving differential equations. So we need an antiderivative of that, or we're dead in the water whenever those equations come up. So here's what it would look like. If you want an antiderivative of e to the x squared, it becomes a definite integral from 0 to x of e to the t squared dt. We change the variable t to eliminate a conflict of notation. Because it's an antiderivative, we also add an arbitrary constant c to it. That's our function. And this works out because if you take that whole thing and integrate from 0 to x, e to the t squared dt plus a constant, this is the check. Differentiate that, then at this line, that's the fundamental theorem, you get e to the x squared. That's an arbitrary constant, so it goes to 0, and that satisfies our check. So here it is, it's an antiderivative. That's extremely unsatisfying, right? Because if you're going to calculate with this antiderivative, well, what do we have for our tools? We can't use fundamental theorem of calculus part 2 because you need a formula that's a closed form formula. All you have is approximation techniques, Simpson's rule, trapezoid rule, to that definite integral right there. Very kind of unsatisfying, but this is what can come up. In fact, if you look at some of the examples in section, I believe it was 9.3 or 9.5, this does come up, where you get an antiderivative in this really bizarre way. So that's our goal in chapter 11. This is not the best way to produce an antiderivative. There's got to be a better technique. And there is. We can be more descriptive, give more information. What we're going for is power series, specifically Taylor series, Maclaurin series, done just right. Will give us a formula for that thing. It just involves infinitely many terms, but it's a better formula than what we're looking at right here. So that's, again, one of our major goals of chapter 11, to do a little bit better than that. Well, any questions, folks, with that discussion here, with where we're going so far? Okay, now chapter 11 is a pretty wild adventure. If you've taken linear algebra before, I think it's comparable to the linear algebra content in just the way linear algebra goes. Linear algebra is highly interconnected with theorems and definitions, and so is chapter 11. It's extremely interconnected. Just to give you kind of a preview of what I mean by that, let's go grab a browser and say sequences and series flowchart. We're getting into these kinds of diagrams. Like, let's see, this is probably a better one. There's got to be a better way to open that. Let's visit there. We're getting into these kinds of things, our sequences, series flowcharts, where we're trying to organize how to analyze a sequence or a series by a lot of different interconnected theories. That's probably not a good one. Let me see if I can do this search a little bit better. Let's go images. I was there. And I think that's the one that I actually use. That's kind of neat in a way. I actually use this one personally in this class. Oh, Pinterest is not going to let us grab the file. Don't worry, I have the file. I'll share it. I don't want to make a Pinterest account just for this. But this is really our content of chapter 11 in our actual book. I'll share the file later on, but I'm only showing this just to give you a heads up of how chapter 11 works. The moment we pick up a test, like test for divergence here, it could be used all over chapter 11. And sometimes we have a test like the comparison test that uses a prior test within the test itself. And so the tests also interconnect all at the same time. So that's the reason we're doing chapter 11 a little bit earlier instead of chapter 10. This work is so interconnected that we really do need to go slow, take our time with it, collect the results in a methodical way, and we'll be in really good shape. This is a good chapter to reread as well. I hate to say that, but it really helps. It's one thing to see this information the first time. It gets your brain all primed with all the different results. But as you go through it a second time, now you're making the connections that you need to make in order for all of chapter 11 to really make some actual sense. So it's kind of a beast of a chapter, but we'll get through it, folks, I promise. Here's how it starts, though. Not bad at all. In order to do that weird thing we're talking about in example 11, get a nice antiderivative, we start our adventure by thinking about sequences. All a sequence is a special kind of function. It's a function whose domain are the integers. So A1 is going to be an output, A2 is an output. The input is the subscript, A1, so 1 is the input to the function, like an independent variable. A1 is the first term of the sequence, A2 is the second term, and so on. And notice we put this ... there. The ... is a reminder that all of our sequences are infinite in length. So all sequences, in this class at least, all sequences are infinite in length. In other words, they have infinitely many different terms. So it's as if we're taking a function that goes like this. F takes its domain, something like the natural numbers, 1, 2, 3, 4, and so on, gives you a real number output. The real numbers are the terms, A1, A2, they can be any number whatsoever. So next, If you write out a sequence this way, that's always perfectly fine. That's how it's been written down in, say, this example right here. But it also could be written as an. The thing in the middle is the general nth term. If we need to say when it starts, we might go from n equals 1 to infinity. Sometimes the problems, even in the homework, might say start at 2 instead of 1. But any way we convey it, we're always just talking about the same thing. Sometimes we just write an and refer to that as the sequence. So just like right here, there's a sequence, an is the output, the n is the input, the index, and we're just taking 1 over n to calculate this. This starts off as pretty relaxing concept, really. It says write out the first 5 terms of that sequence, plot the sequence on the domain, 1, 2, 3, 4, 5, and then we'll just guess at the limiting value. Really, again, it's kind of a get everyone on the same page kind of example. I think this is a relaxing end of the notes. For sequence is just 1 over n, and it says write the first 5 terms. It's referring to a1 as the first term. That would be 1 over 1, or just 1. Second term is a2, that's going to be 1/2. Third term is 1/3. A4 for the fourth term, essentially we're just plugging a 4 here by the red dot, which means in the formula, we plug a 4 there. 1/4. And A5 would be 1/5. It goes on forever, but this is really the first homework problem. Just write out the first 5 terms of the sequence. Then it says plot the sequence on the domain, 1, 2, 3, 4, 5. Well, it'd look a little bit weird. That's part of our purpose on this example. It's kind of a simple one, just so that we can look at all the moving parts. Here's how we would plot the sequence. These are the values n going in this direction. These are the output values, an going in this direction. And when we plug in 1, we got a value of 1 exactly. My scale is unequal, just so that we can really visualize it. So 1 going in the vertical direction is a huge scale, short scale going in the horizontal direction. We plug in a 2, and we got a 1/2 out. But first, we're plotting the sequence, so let's not forget to actually plot it. Notice our function is not a connected curve any longer. We have discrete points in our graph. So A3 gives us a third. This is going to be slightly hard to put down perfectly, so I'll just sort of fudge it. A4 is going to be a quarter, so about here. A5 is a fifth, so right about here, roughly. So this is our sequence. And again, observe that the function an equals 1 over n consists of discrete points. So here's a wild question. Is this the graph of a continuous function? Kind of a weird question, but it turns out it's good call. This one is a no for continuity. A continuous function means we'd have to be able to plot something like this, an actual smooth curve where we never lift up our pen or pencil when we go to plot this. If it consists of just discrete points, we have no notion for continuity. In fact, continuity goes through this. Continuity means you can take the limit as x tends towards 4 of a function and get f of 4. This is the essence of continuity, a direct substitution. But a limit around 4 doesn't even make sense because there's no curve connecting around it. A limit needs a domain going to the left of 4, a domain going to the right of 4 to make any sense of that at all. If it's an isolated point right at 4, then this limit, as x goes to 4 of an, does not exist. So there's no continuity here, and that means the limit as we head to a specific point never ever exists. That's kind of weird. But there is one limit that will exist. We can take the limit as n. Oh, and I did make a mistake here. This should have been an n going to 4, not an x. Down below, we'll take the limit as n goes to infinity of an. This is the major thing that we want to do in this section. We're still going to be analyzing limits. It's going to be limits of functions consisting of discrete points, so it's a little bit weird at first. It'll feel very familiar to Calculus 1 before very long. Limit as n goes to infinity of an is just a limit as n goes to infinity of 1 over n. All I've done is plugged in the actual function. And if you had to look at the chart or the values that we're taking, what would you say this limit should turn into? Absolutely, this is a limit of 0 because the points get closer and closer to the n-axis, height 0, as the index n gets larger and larger. So this has limit 0, and we'd say an converges. It's not an accident we're borrowing the language of converges and diverges from section 7.8 on the improper integrals and bring it into chapter 11. In fact, the improper integrals with domains saying 0 to infinity are there because of these notes. We'll be looking at improper integrals before we get very far into chapter 11. But this is kind of, again, a getting started part of the notes. So we followed this value to the letter. What is the limiting value of the sequence? We got a limit of 0 on this one. Any questions at all, folks, with this one at all? I think I already asked that, but okay. Just for the sake of seeing what happens when something diverges, here's the new one. Write out the first 5 terms of the sequence is what it's asking. But just because we can, let's actually break the letter of these instructions. We can plug in 1 through 5, crank these out. But if you really want to visualize the sequence well, technology is really helpful. So on example 2, let's actually go against the instructions and just use Excel to visualize it. Does that sound all right to everyone? Okay, so breaking our own instructions just a little bit. Here's our new tool. Let me move the participants just a little bit to the right. I want to emphasize too that you never have to use Excel in this class. I will pull it up maybe here or there occasionally, just for the sake of visualizing something. And this is one of those really rare times. What we need is an index n. Next, we need the function an. So here we'll start at 1. Let me try again. We'll start at 1. And we'll take this, add 1. This will be our successor term, a2. Let's do a whole bunch of terms because we can now that we have technology working for us. Let's go to 20 different terms. There we go. To get a formula in, if you decide to use this for the homework, again, it's only for the sake of extra visualization. You don't have to. But if you decide to use Excel to visualize in your homework, here's how you do it. Go equals, put in a 1 for that part of the formula. Then it's going to be plus for this part of the formula here. Go 10 to the power, and you don't want to put in n. Left arrow, a2 is our index n. Then divide by 9 to the power of a2, that's our index n. We get that value out, 2.1 repeating. Then we can just keep on calculating these. Next value is 2.234568. Then we have a 2.3, 2.5, 2.6. And looking at the pattern, kind of hard to tell at this stage if it converges or diverges. So let's keep on going. There's the first 5 terms. But here's the first 20 terms. Putting this into a graph, you just want to select 2 columns and go insert. Look for the one that looks like a scatter plot. This one right here will do just fine. So that's the graph of our sequence now. And looking at that graph, would you say this converges or diverges? Any volunteers on
I'd
Zoom?
say it would diverge to positive infinity.
Yeah, I totally agree. Awesome. Thanks for that, Chris. This looks like a totally divergent pattern. But these things can be kind of deceiving to us. So what we need is some limit laws to help us out for sure. But from this information so far, I mean, we went beyond the letter of the exercise. We went the first 20 terms. Looks like a divergent sequence. So let's copy and paste this in. Okay, so not the first 5, but a whole bunch of terms. Looks like that should just be the next page, maybe. Here's the terms of the sequence written out, the terms of it plotted out going in this way. And now we can say on this one, well, it looks plausible that the limit as n, the index n gets larger and larger going up to infinity of 1 plus 10 to the power of n divided by 9 to the power of n equals infinity. Turns out that is true, and this diverges. So this one will be a divergent sequence altogether. It's all about the 10 to the n divided by 9 power of n. That's really 10 ninths to the power of n, really. It's the fact that that base is larger than 1 that caused it to diverge. Any other questions or comments with this one? Okay, let's take another look at that now that we have technology working for us. We took 10 to the power of n divided by 9 to the power of n. Let's just simplify that to 10 ninths to the power of the index n. So that's our new formula, just slightly simplified is all it is. Let's paste it down. Double clicking like that pastes it all the way to the bottom of the list. And now let's imagine we did change it around. If this was a 9 and this was a 10, let's update that. That's what our picture would look like this time. Looks like it's converging to 1 altogether. And again, it's all because the base here is less than 1. We make it negative, what would you say happens this time? Is this converging or diverging with a negative value? Kind of hard to guess almost, right? I think some people probably are thinking converges, but I think you'd be right. Let's update everything. Put in a negative 9 divided by 10 to the power of n, and this is what you get. Sometimes the terms are positive, sometimes they're negative, but overall, they're getting closer and closer to a 1, still convergent. What would make it not convergent is if you put something like this, 1.1, for example, anything larger than 1, or anything smaller than negative 1. So negative 1.1, and this is our new picture. It's diverging in a totally different way. The points are going either towards positive infinity for some of the terms, or towards negative infinity for other terms. This would be a sequence where we would just say limit doesn't exist. You might say plus or minus infinity to convey the two directions, but there's not as much of a common way to express that. So those are the weird things that can happen with our sequences. And some way, somehow, this weird, totally discrete function, it's not continuous, it's not differentiable even, but it's going to help us get to here in finding an antiderivative where you verify through differentiation. That's really pretty weird. Essentially, once we take sequences and understand them well, we're going to develop them into something called series, and series are a way to essentially connect the dots and get an actual real function out of this stuff. Well, that's how the first examples are going to look in the homework, mainly just playing around with the sequences, deciding what they are. This is kind of a silly exercise. I mean, this wasn't too major. It was more about putting the graph together, seeing the patterns of convergence versus what it looks like for divergence. So that's going to be the picture in our mind's eye when we go to different, more involved problems. But with what we have going on next, the hard questions are to not say what the terms are, but to find a formula for the terms. And that's actually something we do have to do in chapter 11. So this will be an important problem for us. Probably a good stopping point as well, since I think we want to give this problem the time it's due when we come back on Wednesday. Then we'll move through this section of the notes. It's just the good old limit laws and some specialized theorems that we'll do case-by-case examples on to analyze the theorem. So pretty much all we're really doing here is taking limits. And sure, they're not limits of continuous functions, but this should feel a lot like Calculus 1. In fact, a good thing to leave the class with is section 2.6 is very excellent review for chapter 11. The reason for that is section 2.6 is limits at infinity. That's exclusively what we're dealing with here and going to infinity every single time. Well, I think this will again be a good stopping point for us so we can give enough time for that next problem. Any questions or comments at all, folks, before we call it a night? Okay, well, have a great night, folks. Good luck on midterms. When we come back, we'll just be right here in the notes. Probably moving into section 11.2 as well. Hey, questions?
So for 9.5.
Yeah.
When we were in this one. I just asked about, this one, front, 'cause I was just thinking, couldn't you just, divide everything by 4? It's gonna be 1/4 in front there,
Yeah,
and then 3 right there, but then the derivative of 1/4 is 0.
right, but here you'd have a coefficient of 1 other than the 0, and that's what
Oh,
would make
yeah,
it a
true.
problem. Yeah, I like that line of thought, though. That's pretty much what we're trying to do is somehow, some way finagle a product rule getting inverted. Does that
Yeah.
make sense there on that
Yeah,
one?
I was just wondering about
Gotcha.
that.
That's a good thought, though. I like that.